Every journey begins with a single step. For our friend, the hydrogen atom, that step is a bold leap from being part of a water molecule to an emissary of energy. In the heart of an electrolysis chamber, powered by renewable energy, water is transformed. Oxygen steps back, releasing the vibrant hydrogen atom. Alone, hydrogen is volatile, but when paired with captured CO2 and the help of a touch of alchemy, together, they forge a potent synthetic fuel. A new energy carrier, clean, efficient, ready to power our world. Innovative companies are investing in the production of eFuels, which can then be distributed via the existing infrastructure to industry and consumers, providing them with a climate-friendly alternative to conventional fossil fuels. Aviation, maritime, heavy goods transport, even your car, eFuels power a wide range of sectors and offer a sustainable solution to our diverse energy and mobility needs. We at the eFuel Alliance embrace the entire value chain and give it a face and a voice. Our goal is political acceptance and regulatory consideration of eFuels as a significant contribution to sustainable climate protection. In the quest for green energy, eFuels are an essential piece of the puzzle, linking today's infrastructure to a more sustainable future. The eFuel Alliance is powering this transition, forging a path from hydrogen to hope, because the future of energy is now.
Good morning to today's webinar about the impact of the Delegated Act on RFNBO production. My name is Tobias Block. I'm Chief Strategy Officer within the eFuel Alliance, and I have the honor to moderate today's webinar, in which we are presenting a quite interesting actual study about the impact of the production criteria. The production criteria is an enormous challenge for the market development of hydrogen and eFuels at the moment. This is also confirmed by the politics. On September 16, the German Green Economic Minister Robert Habeck sent a letter to the European Commission and said that the production criteria that we will discuss today on the electricity for grid-connected hydrogen production will increase production costs by 2.4 euro per kilogram, which is, from our perspective, too much in the beginning to kickstart the industrialization of the eFuel technology. Today, I have two experts with me from the University of Duisburg-Essen. They have done a study about the impact of the electricity criteria, and I would like to introduce them and then hand over to them to start their presentation. I would like to ask you if you have questions to the study, to the methodology, to the results, please don't hesitate to type it in the Q&A session. There you can also rank the questions. We will try to answer as most questions as possible in the hour we have. And now let me welcome our guests. It's on the one side, Professor Dr. Christoph Weber. He is Chair of Energy Economics at the University of Duisburg-Essen since 2004 and part of the House of Energy Markets and Finance. He has a degree in mechanical engineering at the University of Stuttgart, and his PhD was about consumer behavior and the environment at the University of Hohenheim. With him, he has his research associate, Marco Sebastian Breder. He also has a degree in economics at the Ruhr University Bochum, and he is team leader of energy markets and energy policy. For that reason, I don't want to waste more time, and we are looking forward to the presentation of your study and the discussion afterwards. Mr. Weber, you have the floor.
Yeah, thank you, Tobias Block, this friendly introduction, and we are glad to have the opportunity to present our study, which is also available as a working paper. And you see the QR code already here on the first page of our presentation. It was not commissioned by the eFuel Alliance. I want to make this clear. We did this based on earlier work that we did for the German regulator, where we looked at scenarios for reaching the Paris climate targets at German and European level. And based on that, we developed this detailed case study on the impacts of regulatory frameworks and notably the Delegated Act for green hydrogen. Yeah, and I suppose many of you are aware, but let me briefly summarize what the Delegated Act is, that we have been looking at the implications that but before doing so, let's make it clear: green hydrogen is a major ingredient of European policies for climate neutrality. This has been stated in the Repower EU program and in the European Green Deal. And in the follow-up, then renewable hydrogen has been addressed in the Delegated Act on Article 27 on the Renewable Energy Directive in its second cast. So these rules were formally adopted in 2023 after a lengthy discussion process, and we are here referring to that part of the Delegated Act, which defines when hydrogen can be considered as a renewable fuel of non-biological origin. And the intention of the EU is that this should also apply to international producers, and we will discuss that in more detail. And the key requirements for fulfilling the criteria for green hydrogen are temporal correlation, geographical correlation, and additionality. And in our modeling, as we will see, especially the additionality criterion and the strict linkage between the renewable electricity generation and the corresponding production of hydrogen make a difference. And so our main question that we want to address with that study is whether these criteria have an impact on the ramp-up of electrolysis capacity inside the European Union, and the impact that one would expect when having some additional restrictions in an overall dynamic environment is that restrictions lead to a slow down of the development. And let's have a look at our results. And before going to the results, as we are scientists, we want to start to briefly show you the back of the model that we are using, and also the data and cases that we are investigating before going to the results and coming to some conclusions. And as Marco Breder, together with Julian Radek, has done most of the work on the study, I leave the detailed explanations now to him.
Okay, thank you for the introduction, and thank you to present our work here today. Let's get into this topic. Of course, so what the chair is doing is using energy systems, and for this we need shortly or briefly to explain what this model is doing. And it's called, in short, E2M2S. It is energy to markets to stochastics. That's the full name of our model, and it's a long-term planning and dispatch tool for the European electricity and heat market by the origin idea. So we are able to endogenously expand our capacities in this model, and we are able to simulate 34 European market areas with this model. More technically, it's a linear optimization for selected simulation years under myopic expectations. And what we do in this optimization model is try to minimize the system costs And these system costs are run by investments and fixed costs, but also operational costs. Yeah, and one of these technical highlights of this model is that in order to reduce the computational burden of this big model, is that we apply a typical day approach with which aggregate more or less these time segments, so our hourly, our hours in the full year, what we model, to aggregated typical days. And we also have a stochastic part in this, that we differentiate between different climate years, which has impact on, for example, solar and wind in feed. Yes, this is the left side of the slide. And of course, the topic we want to present needs a hydrogen aspect. And so we integrated this hydrogen market as well. We have a simple market clearing condition in our model introduced, where we reflect that supply must meet demand. And on the upper part of this equation, or this written equation, where you see in blue demand, we take care of that we have exogenous demand, for example, from industry, but also endogenous demand, so from reconversion by hydrogen-fired power plants, but also export to neighboring countries. And this demand must be met by the supply, which is the production from domestic electrolyzers inside Europe, and specifically inside the European Union, but also imports from neighboring countries and imports from third countries outside the geoscope. Yes, that's what the model is doing in general. And we also applied, this is explained later on, different kind of sensitivities for the import prices from third countries, but also quantity limitations, such that you have not only the price of imports from third countries outside the EU and Europe, but also a specific kind of quantity limitation, what you can import. Now, to get into detail, how did we take care of the implementation of this delegated act? So let's call this the regulation here. So we need, first of all, to implement or take care that this temporal correlation, geographical correlation, and additionality is respected inside the European Union. Our solution is then technically to separate renewable energy source technologies for electrolysis. These electrolyzers, which are connected to this RES, can only use this electricity produced then. And these so-called coupled technologies, so for example, a wind turbine, onshore, offshore, or a solar panel with the electrolyzer, is then built in the same simulation year via an assignment set. So this simulation year means that we take care to optimize different years like 2030, 2035, and 2040. You will see this in detail on the next slide, where we present the results. And on the right, in these blue buttons, you see how technically, or in operation research language, this is fulfilled in our model. So the temporal correlation takes care that the electricity consumption for hydrogen production is always lower than the infeed of coupled renewable energy source in every time step. The geographical correlation is respected by these coupled technologies, which are always located in the same bidding zone. And the additionality criteria is respected, that the investments of these renewable energy sources and electrolyzer are always during the same simulation year. So in 2030, for example, that takes care that this 36 months rule is applied. The last bullet point on the left is called assumption. The Delegated Act says finally that we need to respect these rules or implement these rules also outside the EU for those who want to import hydrogen, for those who want to export hydrogen to the EU. We relaxed this for the non-EU members here, so we did not apply the same conditions on the right to non-EU countries. That has one common reason, which is that, for example, in North Africa or the Middle East, so areas with a high potential to produce renewables, these conditions are more or less already met in the future. And for example, a country or an area, the UK, with more fossil fuels today, we see that in our model runs for the years 2030 and also going ahead, 97% of the electricity production is already coming from renewables or nuclear, while gas is only used for peak load coverage. And this has also another reason. We implement a CO2 emission cap in our model, which also limits the production of fossil fuels and also the investment into fossil fuel capacities. So that is the model and how we implemented this regulation. Now, I need to explain a little bit about the data and what we put into this model to calculate our results. And this data is taken from the so-called 10 years net development plan from the year 2022, in short TYNDP. It's from the ENSO-E and ENSO-G. And from this main data source, we use the so-called global ambition scenario. There are different scenarios, and with global ambition, there's a higher degree of confirming to the climate transition path in this scenario data. And from this, we took the electricity and hydrogen demands, the electricity and hydrogen transfer capacities, the renewable energy expansion paths, and the hydrogen export potentials for third countries. We have specific power plant data also introduced into the model, which comes from commercial data. And our model is, as I said at the beginning of this model slides, able to endogenously invest into capacities. For example, renewables. So these are the RES sources, electrolyzers, hydrogen gas turbines, battery storage units, and more. What you see also on the right is this so-called emission cap I introduced in the previous slide. Here you see that we have a sharp drop from 2025 to 2030. And then a more smoothed line between 2030 to 2045, where we want to reach net zero in these sectors in this model. Below is a table where we presented also the demand. As you can see on this slide, the demand is not coming from the Repower EU plan, where we can read that it is planned for 2030 to have 10 million tons of hydrogen domestically produced and further 10 million tons of hydrogen imported. The amount of 322 terawatt hours of hydrogen corresponds more or less to around 9 megatons of hydrogen in 2030. So it's half of it what the Repower EU plan says, but we thought that the data from TYNDP, which comes from national bureaus, might be more realistic than those ambitious goals like in the Repower EU plan. So this is the data. And now I need to explain a little bit about the cases we analyzed before we get then finally into the results. So let me explain the first table from the top. I mean, these are our cases. And in the second column and third column, you see scenario and some short notices and the column case. The column case is the important one. So we distinguished always between the cases base and RED 2. Base is the case where the regulation we are talking about is not in action, while in the RED 2 case, this regulation is in action. So that is what we try to show, the base versus RED 2 case. And then we have in the column scenario 3 distinctions. We have this HP or high import prices from third countries, the LP case, low import prices from third countries, and then we have another further case, the HPLI, which is high prices are assumed from third countries, but also a quantity restriction in the model. Yeah, that we end up in total with 6 different cases we are analyzing, and on the next slide we will discuss this as well. You also see how we put in the prices in the table below for the third country imports. You see that between the left column high import prices and in the right column low import prices, the difference is starting in the year 2030, and it's always around 25 euros per megawatt hour, a difference between high and low import prices. And then for the scenario case where we introduce also a quantity restriction for the imports from third countries, you see in the last table, so at the bottom, the different limits we took from the TYNDP as well. And here you see a huge drop in limits from a huge increase in limits from 2030 to 2035, for example. So what we want to do is to quantify the effects of this restriction and in the interaction between the sensitivities of different price levels and the import quantity restriction. And that is now what we want to introduce. What you see here now is the case where we have high import prices. You see on the left the case where the regulation is not in action in this figure, and on the right, so in this right geoplot, you see where the case where the regulation is in action. And what we can say here is that you see the installed electrolyzers capacities, and they differ between the case on the left where this law is not in action, this regulation, to the right figure where this regulation is already in action. It's for the case 2035 what we analyzed here to show you. And what we can say is that the regulation leads to a shift in the EU from domestic production towards net importer. This means when you look at these red encircled parts that we have for this Western Central European area, a drop by around 15 gigawatts compared to, as a comparison between left and right. And for the Iberian Peninsula, we see similar effects here. So we have lower investments in electrolyzers for domestic production and a larger influence when we neglect these import restrictions. We will discuss the last bullet point later on when we compare all cases in one slide. But that is what happens when this regulation is in action with high import prices here. And these are the capacities which will be installed, so electrolyzer capacities. And now we switch to the same case still, but to the hydrogen balance. So again, in this bar plot on the left, you have the scenario 2035 with high import prices when the regulation is not in action, compared to the right bar figure where this regulation is in action. So, and you see above the zero line in terawatt hours, the sources of supply, and below the zero line, the sources of demand. So this could be domestic production in blue, third country imports in orange, intra-European exchange in green, and domestic demand in red. And what we see here is that the non-EU states are taking on a role as exporters or as transit countries for third country imports. So that is the effect we see when this regulation is in action. So again, the domestic production decreases by more than half in Central Europe, and the same tendency can be seen in the Iberian Peninsula, while in this purple and circles, you see that from the Northern Europe part and from the British Isles, a lot of hydrogen is exported, and most of it is sent to the Central Europe area here. So Central Western Europe, France is also connected to this part. So that is one of our results in this scenario with high import prices, but without a capacity, an import restriction for the quantity. Now, let us compare all the cases. I will briefly explain what you see in this plot. Beginning at the bottom, you see the scenario cases starting from the left with base and red 2 for the high price scenario, then base and red 2 for the low price, and then base and HPLI, which is the high price scenario with import quantity restrictions with base and red 2. So the regulation is in action or is not in action. And we compared the year 2030 and the year 2035, so the development. That is the structure of this graph and of this figure. And you see here specifically the electrolyzer capacity in the European Union. So that is now important that we only look at the European Union in 2030 and 2035 by technology combinations. And what we can say about these results in comparison is that we face import limits, that the import limits drastically increase the domestic electrolyzer capacity. So that is what you see on the very right of each of the years. So these bars are much higher, around 100, between 160 and above 180 gigawatt. And across all scenarios, we see a lower domestic electrolyzer capacity when the regulation is in action. So that is if you compare the base cases on the left always against the red 2 cases right next to it. So these bars are always lower when the regulation is in action. And with these different colors, you see the combined technologies in order to fulfill the additionality criteria, which could be photovoltaic, wind offshore, and wind onshore connected to the electrolyzer. But the final statement from this slide is then that across all cases where the regulation is in action, we see a dominance of wind onshore. So from our cost minimizing approach, this is the most preferable technology in comparison over all cases here. Then this is the electrolyzer capacity. And we also want to explain some effects regarding the electricity sector. Here on this slide, the structure is the same from this figure. But you see now the renewable energy source capacities by technology, again in the European Union between 2030 and 2035. And what we see here is that offshore wind becomes more important as coupled technology only when import limitations are applied. So that is these bright blue areas on the very right of 2030 or 2035. And what we also observe is that, and that is the reason, so due to its lower full load hours, photovoltaic is generally used for general electricity production and is not that attractive for coupling with a capital-intensive technology like electrolyzers. So that's one outcome of our case and of all cases here, finally. Now, we also created a plot to show you the hydrogen balances of all cases. So again, it's the same structure. We have the cases in the same order, and for 2030 and 2035. And you see here, again, only for the European Union, the energy balances. So above the zero line is the supply, and below the zero line are the demand sources. And even if you see these European imports in gray or European exports in yellow, yeah, that means that we are trading with non-EU countries here. But let me explain the main statements from this figure. The distribution of hydrogen supply sources differs substantially between the three scenarios. So that is, for example, with high import prices, of course, the advantage to simply import hydrogen from third countries is lower compared to when we face low import prices. That makes sense. But when we implement quantity restriction on these imports, we also see that the amount of domestic production, so that's the blue bars in the cases with base and red 2, high price LI, so import limits, and we see that domestic production in blue plays a major role in these scenarios. But anyhow, the domestic electrolyzers contributes less to overall supply when this regulation is in action. And finally, the reconversion, so the reconversion of hydrogen to electricity depends on the import prices rather than on domestic conditions here. That is these orange bars at the bottom of each of these scenarios, and you see, a minor but significant difference between the high import price scenarios and the low import price scenarios here. And this is the part of our results, and Professor Weber will make some statements about the conclusion here.
Yeah, thanks, Marco. And to wrap up, I hope we have made clear that, well, we are using a dedicated model, but as every model, there are some limitations. And but we believe that the model captures key features that are relevant to assess the effect of regulations. And so our key findings are that the RED II restrictions lead to lower investments in electrolyzers in the EU. We also see across our different scenarios that the development of the hydrogen market and also the electrolyzer capacities is strongly sensitive to import price levels. And obviously, our first assumption is purely to say there is a uniform price at which hydrogen can come from outside the EU or the modeled area in Europe into Europe. And this is rather challenging assumption. Therefore, we also looked at that scenario where we limit the quantities that can be imported, and then we see that the effects on domestic production are somewhat weakened. And in the time range that we are considering, the use of hydrogen for generating backup electricity does not play that an important role in the total hydrogen balance. Overall, our caveat is, as usual, model parameters drive results, and so you should not take these as absolute numbers, but rather interpret it qualitatively regarding the impact of regulatory frameworks. And what we believe is important to be aware to do assessments against a different set of input parameters, because we have considerable uncertainty how the global markets will evolve over the coming 10 years. And so in terms of policies, I think the implications are clear. The ramp up of domestic hydrogen production and electrolyzer capacity is hampered by the Delegated Act and its provisions. And so the implication is that at least the EU should monitor the ramp up, and we see that this is already happening, and that policymakers in Germany and Europe are questioning whether the current framework provides sufficient incentives and the right incentives for the future use of hydrogen. Also, the EU policymakers and the German ones in particular should be aware that we have overlapping regulations, and so we not, as economists, believe that the carbon price should be the major instrument to guide investments in a low carbon future. But we have other restrictions, and so this has to be monitored carefully, that there are no contradictory incentives set by different regulations. Obviously, besides the objective of climate neutrality in a world with global tensions, also at least a certain degree of autarky at the European level in terms of energy matters is considered important by policymakers, and there also one should be aware that imposing restrictions on green hydrogen that are beyond just that the overall emissions of the electricity sectors are limited by the CO2 cap. These additional restrictions may be counterproductive also with respect to that goal. So there is a trade-off, and we hope that with our analysis we have contributed shedding some light on the trade-offs between stringent decarbonization and rapid ramp up. And with that, thank you for following, and I'm hoping that we have a good discussion right now.
Yes, thanks a lot, Mr. Weber. Thanks a lot, Mr. Breder. I think it's clear that these restrictions make the achievement of the hydrogen strategy goals and the REPowerEU goals quite difficult, and at least from our position as eFuel Alliance, we are clear that we need to revise them, as Mr. Habeck has also proposed. I also would like to thank you, Mr. Weber, that you mentioned that there's no connection between you and the eFuel Alliance. We just give the platform to inform about the study. We're not involved in the study so far. We have received a few questions in the chat. I would start with the methodology questions. Sorry for that. Greg Archer from the fuel company LanzaTech is asking if the model incorporate the 2040 90% reduction target. Also, what assumptions have you made to build the effects of the RED II Delegated Act in the model? I don't know, maybe Mr. Breder, could you briefly sum up this question?
Yes, I guess this 90% reduction target corresponds to all sectors, the overall goal, right? Yes, this is more or less implemented while we simply focus on the electricity, heat, and hydrogen markets. So that's a minor part of this bigger goal, but this is implemented, and we showed this with our reduction passes, so the CO2 caps. And regarding the second,
just to make it clear, the results that we showed were not for 2040. We focused on 2030 and 2035. Also in the working paper, we said that makes too much details if we look at many years simultaneously. And yeah, do you want to continue on the second part of the question? The modeling of the restrictions was that basically we define combined technologies, and there is a joint investment into electrolysis capacity and corresponding renewable capacities, and only the hydrogen that comes out of these electrolyzers is then considered as green hydrogen.
Good, thanks. Thanks a lot. There's another question about the transport for the import of hydrogen. Is it assumed as hydrogen, or do you include derivatives like ammonia, or you don't care and it's just about the price? Have you done some assumption here how the import will look like?
Yes, within so the data from TYNDP, so these hydrogen transfer capacities are based on pipelines, and for the third country imports, our assumption is also based on the TYNDP, and these prices might be. I'm not into the TYNDP right now in detail. Might be that these are derivatives like ammonia shipped, but maybe in pure hydrogen in liquefied form. I'm not sure here.
So in fact, we are agnostic about the import routes. We are running currently another project where we are building up a model of a global hydrogen supply and transport chain, but that's not a part of that study. And we have still only very preliminary results on that work. So I'm aware that this is a critical question, especially for overseas transport. But that was not within the scope of this study.
Yeah, I also think it will not change the results if it's now liquefied hydrogen or ammonia being imported, if the price for the imports is similar to what you have shown. An interesting question, which also I have noted, is if you could say what has the most impact. Is it additionality? Is it the temporal correlation? Is it the geographical correlation? Can you give in your analysis a ranking about this has more restrictions, this is more reducing the capacity, or have you not analyzed the sensitivity?
Well, in fact, the way that we have modeled it, I would argue that we have, with these combined technologies that we implement, we simultaneously model the fulfillment of the three criteria. If these would be disentangled, on the technology side, I'm not sure what that would exactly mean. Basically, probably that you build electrolysis capacities and then you contract some electricity procurement contracts which fulfill then the rules in place. And I think in terms of the overall electricity system, the temporal correlation is one that is, on the one hand, seems reasonable to us that you produce green hydrogen when you have excess green electricity and not in periods where you are running your backup power plants. But on the other side, and that was the argument I made on the conclusion slide, I would argue that the prices on the electricity markets inside the bidding zones reflect the degree of low carbon electricity in these bidding zones at that precise moment in time. Marco, together with another colleague and me, we have also made another analysis where we looked at separate bidding zones inside Germany, very controversial topic in German politics, but we showed that the incentives for investing in electrolyzers would be much bigger for the northern zone if there was a zonal split, and at the same time, even without imposing a strict additionality criterion, the resulting carbon intensity of the produced hydrogen would be rather low, because the electrolyzers are operating when electricity prices are low, and electricity prices are low when we have excess of renewable electricity.
Thanks a lot. I think that's also in line what the German economic minister Habeck has proposed. He proposed to postpone the additionality until 2035 and continue with the monthly temporal correlation until end of 2031. These are the two proposals, and there's an interesting question. I don't know if you can say something to that. Have you presented the results of your study also to regulators, to German regulators in special, and could you say what their feedback is?
Well, when we talk about German regulators, we have to distinguish. We have the BNetzA, which is the regulator of the grids and also plays a more and more important role in all transition planning, coordinating grids, and also generation expansion. And there we discussed earlier versions of our model regarding achievement of the Paris climate targets, but we did not discuss with them the detailed impact of the RED II regulations. And also regarding the Ministry of Economy, which takes the general political role of setting the rules, or at least proposing the laws that are voted by the parliament. We haven't been recently in contact with them on that topic. And others, yes.
Can you say something about the increase of production cost? Mr. Habeck said 2.4 euro per kilogram. Have you analyzed this in your study as well?
Well, basically, since we impose an import price, the import price sets the upper limit for the production costs inside the EU. And so it's difficult ex post to extract an information on additional production costs. So since we fix the price, we make then a statement about the quantities that result, and there we see the clear effect that the quantities go down roughly by 50%, if not more, if we impose the regulation.
Okay. There's a question from Corinna Jörling, if I'm not mistaken. She works for the NOW. which is connected to the German Transport Ministry. She is asking about the scenario without the delegated acts. Does it mean that you have not assumed any sustainability criteria here?
We have assumed an annual CO2 emission cap in each of the model years, which to our understanding is the key sustainability criteria. Well, you should extend it to greenhouse gases in general, but yeah, in view of climate neutrality, that's the key sustainability criterion, which obviously should be applied at the global scale and not only at the European scale, but yeah, that's another challenge.
Is it the threshold of minus 70%, which is set in the RED II, or an overall GHG reduction goal?
It's a cap on the emissions from the electricity and connected sectors, and we haven't modeled the other sectors like transport and heat explicitly, but we have made a top-down division of our overall budget, allocating only a restricted share to the electricity sector, and assuming that the electricity sector has to be a front runner in decarbonization, because it's more difficult to decarbonize heating and transport.
Perfect. There was one question from the journalist Rainer Lütkehuus. He's working for Energate, I think a well-known paper in the energy business. But we have already discussed what of the three electricity criteria has the most influence. Mr. Weber, it was, from your perspective, the temporal correlation and then the additionality, right?
Yes.
Perfect. The first question came not on the electricity criteria, but on the second delegated act. We have not talked today about a further delegated act that we have on CO2 sources. There's a second delegated act, which is defining the GHG reduction methodologies, so how to calculate the carbon footprint of RFMBOs and recycled carbon fuels. And here also different CO2 sources are regulated. For example, industrial CO2 sources are just allowed to be used until 2041, and industrial point sources have to be in an effective carbon pricing system, which should be similar to the European emission trading system. The problem is that this does not exist outside of Europe, which makes imports of hydrogen and eFuels difficult if that CO2 source is chosen. From our perspective as eFuel Alliance, this might be even more important and more restrictive than the electricity criteria we have discussed. And we think at least unavoidable CO2 emissions, for example, from cement plant, pulp and paper, ceramic production, steel, where it is not possible to avoid industrial CO2 emission on site, should be allowed. Do you have an opinion, a position on industry CO2 emissions here?
I think that's a critical point, and I agree that this is particularly relevant for imports of e-fuels. Inside the EU, perhaps a rather superficial reading of the second delegated act is that it has some internal theoretical consistency. That does not necessarily mean that it's practically implementable or useful, but saying if I take the CO2 emissions of a cement plant to make e-fuels and then I burn the e-fuels, so the CO2 emissions of the cement plant have been temporarily avoided, but not definitely. And so this is acceptable, but it's not. And then the cement plant should still pay with CO2 credits or allowances, yeah, so that the overall emission cap set by the ETS is not overrun. And I agree with you that as long as we don't have effective emission trading systems outside Europe, perhaps with some emerging exceptions in parts of the US, like California and the Northeast, and China, I understand, is also doing some experiments on that, but yeah, they are far from the status that the EU has reached over in the last 20 years. And yeah, so that will be difficult. But anyhow, global stringency of climate policies, it's something very urgent to work on and very difficult at the same time.
Yeah, we also see that in the US, the Delegated Act on Electricity Criteria is some kind of copy-paste, sometimes even more restrictive. I think the temporal correlation is hourly from 2028 on, at least that's the first draft. It's still in a consultation period. I heard it should be finalized by end of this year, but yeah, maybe we have to see first the US election next week before we get a final result. But it shows how important the European regulation is, and other markets could take an example which is good or bad, depending on the restrictions and cost increase that we have discussed. One last question I would like to take in is from Reinhard Otten from Audi. He is asking if higher H2 production in Europe increase prices of green electricity and reduce acceptance of heat pumps and electric cars in the EU.
I would say we haven't investigated that numerically. Theoretically, you can make that argument. It strongly depends on the assessment of the renewable production potentials. And yeah, when you look at wind onshore, what we have observed in our numerical analysis recently, there is a gap between what many potential studies say that could be used as areas in Germany or other European countries, and what is effectively available for investments, because those administrative entities that are in charge of making the spatial planning, Raumordnungsplanung, they are in some German states, but also in other European countries, quite restrictive in assigning areas for wind energy production. And if we have these tight restrictions on the potentials, then and this has an effect on the electricity prices if we have more demand for green electricity through green hydrogen. And that's then in principle the advantage of open markets, that the markets will decide where it is more cost effective to produce e-fuels or green hydrogen. Is it inside Europe or outside?
Perfect. A personal question from me. Do you think it's fair that hydrogen production has these restrictive criteria, but other electricity consumers like heat pumps and electric cars can use any kind of electricity?
Well, I think what we see is at the moment that they can use any kind of electricity, but the electricity is rather expensive, and so that reduces the incentives to switch to heat pumps and to electric cars. And I think we really have to work on making green electricity cheap for all usages, and then additionality criteria are second order concern.
Perfect. There we definitely agree. Expansion of renewable electricity generation is key. for everything, for direct electrification like electric cars, but of course even more for more inefficient technologies like hydrogen and eFuels. So let me wrap up. I think that was an important webinar. We have shown a scientific study about the impact of the Delegated Act, mainly on electrolysis capacity in Europe. We also have seen that, for example, funding schemes like H2 Global are struggling. They have not managed to get successful auctions for methanol or synthetic kerosene. And often the feedback was due to too restrictive delegated acts. At the same time, right now, the Delegated Act for Low Carbon Fuel is on the table. And we see here that the Commission is proposing additional CO2 sources. That at least means from our perspective that also the RFMBO Delegated Act should be revised and reopened. In the chat, you have our latest position paper on market challenges, and the delegated acts are one of the most important challenges for an uptake of the e-fuel market at the moment. As eFuel Alliance, we try to have a more pragmatic approach. I think we cannot afford these restrictive criteria in the beginning. We are looking forward to the hearings of the new Energy Commissioner, Dan Jørgensen, next week as well. He has got questions on the delegated acts, so maybe there will be a signal indication if the Commission is willing to revise the delegated acts. From my perspective, if we see that something is not working, we really have to fix it. For that reason, I think we need to revise the delegated acts. We need to make it more pragmatic, especially in the beginning. On long term, there's no question that we need clear sustainability goals. So thank you, Professor Weber. Thank you, Marco Breder, for your presentation. And I wish all our participants a good week and see you to the next eFuel Alliance webinar. Bye-bye.